Okay, guys. So today we are literally halfway through where we should be for prototyping and building. So you guys are starting to get approvals on stuff. So if you've gotten approval already, awesome. This is kind of like December in Capstone, which means nobody has an approved project. Nobody's got a clue what they're doing. Some people have mentors. No. It's about that time where everyone's thinking about going on break and doing nothing. In Capstone, that's dangerous because you're going to be gone for a few weeks. You actually want to have your ordering done by now. And that way, if you are around or have a teammate that's around, you can actually get some testing in. The break is actually a great time to get into the labs. And on campus, if you need some other facilities, it's a great time because everybody's gone. You can actually get a lot of your stuff done. You can do your first passes on your DOEs and testing your prototypes and seeing what's going on. If you wait, what happens is you get back into the semester, you get your first DT from Capstone, you're now swamped with paperwork instantly. You're starting all over again, actually. In Capstone, you put together one binder that's 5 inches of paperwork. Second semester, you put another 5 inches together, and it's the same stuff, but more. It's actually usually about 50% more crap in it. You may reuse some of your papers, you may reuse some of your standards, some of your patents. So you actually filter those down, but the homework starts to scale up. So it ends up being a lot more work the second semester on paperwork. If you waited to buy your stuff, now you got probably a 2-week delay on ordering. You're gonna have to sit there and wait for the stuff to get received. So you basically instantly gave yourself 2 weeks off to wait another 2 weeks. So now you're a month off of where you could have been. It happens really fast, and it's just, it's human nature. It happens every year. And that sets up this thing Dr. Pizzicone likes to call March Madness. It's literally March, and you guys are going flipping mad. There will be 24/7 in the space people trying to get shit done in a frantic hurry. If not, you're even going to be in worse shape. It's a really painful time. It's very stressful. It's usually where the nuclear events on teams pop up. People will just start arguing over anything. It sounds like a bunch of married old couples. It's reality, and that's why I try and teach the team dynamics. You want to sort that crap out now. You want to get your shit ordered now. You want to start building and testing your stuff now. So we're literally at that point right now in this class. And you can see right in the order, we're hopefully getting into the alpha beta, more on the beta side for everybody. We're going to go a little bit over final deliverables because we're getting close to that time too. Pizzicone will wait until like the last 2 weeks of Capstone in the second semester to tell you what that is. We like to tell you at the front of it. So basically, what do we expect from you guys? We're going to go through the DOE, and I'll try and make an analogy for Capstone so it hopefully simplifies things. For that, I'll probably need everybody in the team that's game mechanics person to come on over after I'm done lecturing, and I'll kind of help you up a little bit further along. It'll explain some of the DT5 expectations. It'll also hopefully help you for Capstone. If your design mechanic person is not here, your game mechanic person is not here today, so the team leader should come over, or someone else. It's going to be important for you guys to get your homework done. DT4 is done. DT5 is not due next week, but the following week. So that'll give you time to work on it. Final stages on verification. You guys know these, so just remember these are the good questions to ask yourself. Besides, also, would you buy it? God, that is dark. Can't see that, but that's basically. We'll go over DT5 in a bit. The final deliverables, November 6th. Okay. The most important part of this, your final deliverables, are going to be files that you want poster printed. We use Platinum Printing. They get a high quality print job on the artwork. The stuff will look awesome. We need to get all the stuff from you right on that day because we have to kind of assemble it into this long poster. We'll get this 30-foot ream of stuff of everybody's crap on this one piece of paper, and we want to make sure that we tightly pack it so we don't pay for white space. We've done that a few years in a row, and it's just a waste of money. Other things that are going to pop up, and we'll talk more about it next week, Nicole will, is bill of materials. Kind of thinking about the other things that you got to turn in. Anybody here doing 3D printing or want to do 3D printing on their game? Okay, so you're going to be pestering Steve. Anyone wants to do laser cutting or anything like that? Okay, you guys will probably be pestering Brian and Garrett. Anyone else doing sculpting or casting or something like that? You guys are going to be pestering Blake. Yeah, so we need to know that and kind of stagger that. We also want to give you an idea of if you're going to 3D print stuff, if you're thinking about 3D printing 50 of the same things, yeah, we may want to do a few of them and we'll cast the rest. And that way you have more options in case like later on you want more or something like that. But we'll talk about that pretty quick. Getting these files to us early allows us to look them over and give you guys some suggestions and kind of help you make that game look better. How many people have an idea of a game box cover? Okay, so we'll do that too. Okay, cool. So we'll start thinking about stuff like that. In fact, next week I think Garrett is going to redeem himself finally. We'll have to bring in Garrett's box, by the way.
I think he destroyed the other.
Oh, really? Oh, man. This guy's used every tape, glue, and adhesive known to mankind to put together a box that fell apart. Now, that's actually pretty rugged, right? I mean, you could have stepped on it.
It was mostly glue.
It was mostly glue, yeah. So, yeah, he's going to redeem himself this year and show you guys how to build a box. Make it a little bit higher quality. We're going to go through financial plans. That's where Nicole's coming in. We're basically going to scope out the prototyping costs, what would it have cost you to make the game. That's something that the people will ask you sometimes, but then they may ask you also what's your production cost. Two very different numbers. Michael Coe, who will be here, he'll talk about that. He'll say it'll cost you about $300 to make a prototype game. Are you going to sell a game for $300? No way. Yeah, you're trying to get that cost down to about $4 a game. And then you're going to raise it back up to maybe 20. But we'll go through those different rubrics too for you. In Capstone, we'll go one step further also. We'll do net present value, which is if you were going to sell your business or the game concept, what is the value of that? And that's what in Capstone you have to do. So we'll give you spreadsheets for all this stuff. Make sure you have a name of a game, all the basic stuff. We'll go through, basically it's an elevator pitch. So probably, I don't know, Nicole or Steve, is it next week we may want to rearrange the tables, or is it going to be the week after? So if anyone wants to practice a pitch. Open labs? Okay, so like in 2 weeks, somewhere in there. Okay, so we'll kind of get you guys laid out in a fashion that you will be on the final day, and if you're ready to practice your pitch, you can run it by us. Highly, highly recommend writing it down first and then practicing it. And then just don't forget, you got your killer points. What's your, what was that perceived market, the need? What was your unique solution? What makes you different than the competition? Who are the competition? Throw us some financials and what you guys are doing for a game. Kind of like a little bit of the game mechanics or something like that. And I'll, basically the game mechanics, when people show it off, it's kind of neat that you could set up a board, and on one half of the board you could show one sort of thing, maybe it's movement mechanics. On the second part of the board you could show another aspect of the game. All just one layout. You could quickly show two different things that really are maybe your blue ocean diagram points. The bill of materials, literally think of it, it's like every little thing that goes inside that box. If you open up most games, they'll have the rule book, they'll have components. That's basically a bill of materials, start of it. Next thing on there would be, where would you buy it from? What would be the cost? You want to kind of have that information, and that'll help you set up all these other financials. Think about what goes inside of a rule book. Look at a few of them. You got things like pictures of the game mechanics, anything that's really hard to describe. Take a photo of it and put arrows on it. Whatever you got to do. And in a sense, that's kind of like the documentation process you got to put together in Capstone anyways. So the more writing you do, the better. And one of the games that we made in the class, this was mostly almost all made by Platinum Printing. And what we did is we just took boards that were all cut from tiles and we glued them onto a poster board, chipboard coins and tokens and things, double-sided cards. Almost whole game made by just simply Platinum Printing. You got to have, I don't know, I must head back. Your rules, you want to kind of do that on 8.5 by 11, 11 by 17, staple it, whatever. Make sure, you got something in there that's descriptive. Your components, are all in there. If there's anything, neat or unique, you got to tell someone. You can have examples of gameplay in the rule book with photos or not. I think we'll probably go in a little bit more detail on these, but, definitely, Steve, what's your favorite? OBJ on 3D print files? STL? STL? You guys are all using CorelDRAW for laser cutter, and not much else that we got to really comment on. If you want things for printing, it really helps us if you put it into a PowerPoint. So what Platinum Printing does is to take a PowerPoint and put it into a PDF, and allows us at least to move blocks around and try and get rid of this dead space. So this is like an example of one game where we threw everything together, onto different sheets. This one, I think this was the example where we goofed up. This sheet, this sheet, this sheet were perfect. This sheet was actually just like that much. We paid for a piece of white paper that big. It was like maybe about $60 we paid for right here. That kind of sucks butt, so let's not, we don't want to do that again. If you guys want to professionally have your cards made, we can do that for limited copies. It's something like $14 to $20 per deck of cards. It's a little bit expensive, but we can do that if you'd like. It's a little bit easier that way. If you want to sit there and upload all your images and things, it's a little bit of a pain in the ass, but if you want to do it.
Can we, if we only have like 10 cards, we can download within that?
I don't know, because usually when we've done them before, we've done like the whole deck, and it's a deck of 52. So we might have to check. I mean, the other thing you can do is make extra ones, and basically you make a single deck of cards, but you got 5 copies of it. And that's not a bad thing to do, because one of the things we haven't really done is figure out the statistics of our games. And one of these days I would love to do that, but how much variability in gameplay you have. And that's kind of like what we want to see you guys sort out now. But the more you play, you figure out, oh wow, we need a few more of those cards. That might not be a bad thing for you to do, is just have one deck of cards that's 5 copies. So, and then, you could keep one at that point. Another thing that we've kind of identified in the curriculum as a problem is design of experiments. We have you guys do this in capstone, and what we found out is nobody's ever done one before. You may have heard it in statistics. Has anyone run a DOE before, design of experiment? Okay, we got 2 people. Anyone ever just on paper set one up, besides the 2 people? No? Okay, so we're going to do that here in this class. ABET requires it. It's actually something industry requires now. I've seen it pop up at Medtronic, Bard, Gore, Intel. People in the field want DOE to be something that you guys come out of here knowing. DOE was started by a farmer or a plant biologist. His name was Fisher. He had a farm, and he was trying to figure out how did he increase his yield, crop yield. And he looked at it. He was kind of a middle-aged guy, I guess. And he looked at this field and said, I don't want to be here forever changing my field's nutrients in the soil 10 times, because that's 10 years of waiting. And I also want to see what the effect of temperature or maybe light quality or water is on that. If I did it all at one of those levels and then waited a year, do it again, and do it again, you can kind of see where it's going. The guy's going to be dead before he figures out what really makes good crops. So he came up with the idea of dividing his crop into 4 parts. And what he would do is vary all 3 of the conditions he was interested in. And if you do that in a sense of a high and low, you basically have a 2 to the 3 or an 8 level design. And he came up with a statistical method of actually running only 4 of those and getting enough statistical information out of that to figure out what was the most important thing for his crops. Or, it was really a neat thing, was if any 2 of them interacted and made an important effect that he wasn't aware of. And it was a really quick way to run some experiments. And it's a very useful technique now. The engineers took it over. Intel does it all the time. They love it on the process line. We actually have one of the world's leading experts, Doug Montgomery here at ASU's Industrial Engineering, teaches this stuff, wrote the book on it. He'll teach you how to make the best martini in the world in his class if you take it. It's a great grad class. Or if you like golf, he'll teach you how to not drink a lot while you play golf, because he ran that experiment too, and he found out he got worse as he played. And so he's got like really fun experiments he's done. But it's really fundamentally like the best things that you can do when running an experiment. His view of statistics is if he had like an hour left to live, he'd go sit in a stats class because it'd feel like twice as long. So he doesn't like math, but he likes the idea of designing good experiments. So it's really a reflection of how to just design. It's kind of just, we kind of do it in capstone too with needs identification or a problem statement. You got to start off with a good problem definition. Then you have to go through some sort of design process of not like designing something, but designing a good experiment. And I'll show you one of those. And then eventually you got to do your stats on it. I mean, the math is there, and make some sort of conclusions. There's a lot of things there's a lot of terminology in it. So the 2 to the 3 experiment that Fisher ran, it's a factorial, 2 levels, a high and a low. The factor is the thing that you're trying to study. Does it have an effect? Does light affect my plant growth? Does soil content? Does water? The responses might, in his case, was the crop yield. Did I grow a lot of whatever he was growing? I don't know. The level is how far apart do you, what is that level? Is it no light, a lot of light? What is that? There's a lot of things you got to do that are really important there. You don't want to pick 2 factors that are 2 levels that are so close together that you can't differentiate an output. It's like same response. You could spread that out and it's still, no response. But you want to kind of like do a failure mode where you pick a level that's bad, pick a level that's good, and you can see the effect real easy. A center point is if you do a middle point. So if you had something where it's 2 bad things, you could pick a center point that's really good, and you get to see some nonlinearity in your model. It's actually really important. Replication, obvious. OFAT, that's my sister. OFAT is 1 factor at a time. I give her shit all the time. OFAT is 1 factor at a time. That's why I was describing what Fisher was doing in the beginning. I'm going to run this at no light. I'm going to run it at 10% light. I'm going to run it at 20% light. I'm going to run it at 30% light. It's typically what a professor will do to you. Run it at 100 different variables and let's see what happens. And then, that was at the 1 temperature. Let's change the temperature up 2 degrees. Then a week later, it'd be like, let's change it up another 2 degrees. OFAT is really painful. The hardest thing with OFAT is to go back now and look at all those experiments that you ran weeks or months apart and try and correlate them together because time might be a factor. Best guess, my favorite's SWAG, scientific wild ass guesses. You got to start with somewhere. You got to have some a priori knowledge or just take a wild ass guess and just see what you can come up with. Residues, it's just getting into the analysis. I'll show that later. Blocking, that's the thing that you may have to do with time. Intel, when they run DOEs, they like literally set up their fab and they run this 1 condition and it's everything they can do and it takes a week to see the output. Then next week they run another series of conditions. Then the 3rd week they run another series of conditions. Time is now blocking that experiment because they've done things weeks apart. Maybe new people on board, there may be different people working that day. They may have different chemicals in the process now. There's a lot of things that you have to block, and it's actually a statistical way of separating those factors, maybe factors, and seeing if there's a real effect there. ANOVA, wasn't that a rock band or something? I don't know. ANOVA is the statistical math behind all the magic, which is Excel, MATLAB, or there are some SAS and other statistical packages out there. Don't do math. Randomization, that's kind of like what goes on in my head all day. No, randomization is really critical if you can do it. If you can do it, it's probably one of the most critical things that you could do because in the essence of running the experiment, doing 1, 2, 3, 4, 5, you may actually be inducing a response. So you want to randomize as much as possible. And you guys know what t-testing is. And factor interaction is really cool. Factor interaction is like, if I had a high, let's see, what would kind of make sense? If I had low light quality and high temperature, could that be the same as having a low temperature and high light quality? Would the plant still grow? Maybe. So the interaction of those 2 factors, even though they change, actually produces good yield. It's kind of a, something that could be important. This is really a bad example of an OFAT because no faculty in the right mind would ever say just run 3 levels. I'd probably say run 10 levels. So if we said 3 times 3 and times 10, you can see how the math gets really bad fast. If you come over here on DOE, you can run this much complexity, which adds 3 center points, and you can be down to 27 experiments. There's another technique that Fisher did where he ran only 4 of the 8. That's called a half fractional. So that takes half of this 8. So it only runs 4 times 3, 12, plus 3, 15. If you're really cheap, you could not replicate all these conditions. You can just replicate your center points. So you could actually run 4 experiments, 3 center points, have 7 experiments, compared to maybe 90 over here. So you can actually run a lot less experiments. More importantly, over here with that kind of experimentation, I have statistical analysis and knowledge of my experiment. And I can actually tie back factor interaction, which you can't do over here, unless you see hyperbaric math in your head all the time. When you get to 4 factors, it gets, just goes out of whack real fast. Neat thing with 4 factors, you can get down to quarter fractional. So instead of running 16 experiments, you can only run 4. Still get good statistical analysis out of it. So it gets really powerful as you get going. And there's, obviously some of the benefits. that I mentioned. So unlike my favorite programs, this is only a 7-step program. Gosh, you gotta wake up, guys, come on. No, so you gotta start off with recognizing the problem. It sounds stupid, but it needs identification is still in the nation a problem for engineering. That's actually red flagged by National Academy of Engineers, red flagged by our ABET accreditation people. It's one of those things where we're trying to figure out what is the problem, and stating it properly is a challenge for faculty to teach and students to learn. And so in DOE, it's one of those things, there's an iterative step here. Choosing your factors, levels, and ranges, I kind of already mentioned a lot of the challenges there. Selection of the response variable, what are you actually looking for? How are you actually going to measure it? What are the units? That part right here is the iteration. You really want to go, after you pick out what's my response variable, go back and say, is that really going to answer the question I'm trying to answer? Choice of the experimental design is kind of, are you doing a factorial design, half or quarter fractional? Am I doing center points or other data points in there? Am I replicating? What part am I replicating? Where's my randomization? Step 5 is actually perform the experiment. At that point, Doug would say stop, because if you did that much, you ran a really good experiment. My world is, if you did that once, you probably chose something wrong. Maybe it was a factor, maybe it was a level. The second time you run an experiment, you probably did something else wrong, like my test apparatus was, goofed up and I got to redo it. The third time you run a DOE is usually your best damn data you'll ever get. It literally, like every DOE I've ever seen usually takes 3 runs. Senior year, how many DOEs do you think most teams run?
40.
They don't have time. Remember they took break off, they came in, ordered their parts, waited